Let's revisit our M&M colors question using a different question this time. We've seen that there's strong evidence that we don't have the same proportion of each color in our M&M population. Now let's look at what the M&M Mars Corporation tells us is the actual breakdown of M&M colors. This is no longer from our sample. This is published from M&M Mars. They say that they, at their plants, produce 24% blue, 14% brown, etc. Mix them all up and separate them into bags. We can assume that this process is pretty close to random. So in StatKey, we are going to return to the chi-square goodness of fit page from our previous example because we've already entered our data set in there. So we're using the same data set again, but we're going to enter these for the null hypothesis. So here in StatKey, this is where we've already entered our M&M data. We can see our data set over here. I'm going to reset the plot and click on null hypothesis. And instead of having all of these default equal proportions, I'm going to overwrite them with the proportions we're given. 0.24 for blue, 0.14 for brown, 0.16 for green, 0.20 or just 2 for orange, for red 0.13, and for yellow 0.13. Now my null and alternative hypotheses are a little different. My null hypothesis is not that the proportions are equal to each other, it's that the proportions are equal to this list. So I will just reference the list, or I could even just describe it. Proportions are equal to the list above. My alternative hypothesis is that at least one of these proportions is different from that list. Now I'm going to calculate my expected counts by taking each of these null hypothesis proportions of the total. I can't really do the 90 divided by 6 now because they're not all equal proportions. But for example, I'm told under the null hypothesis that it would be 24% blue. I know I have 90 M&Ms, and therefore 24% of 90 is going to be my expected count. So to calculate that, I'll do 0.24 times 90, and I get 21.6. I'll just take everything out to the tenths place for this. For brown, I have 14% brown, so I'm going to take 14% of 90, which is 0.14 times 90, which comes out to be 12.6. And the rest of them are done for us because we can see that it follows a very similar pattern. Now to calculate my chi-square test statistic, I'm going to follow the same formula, but my expected counts are different from what they were in the previous example. So it always goes, remember, observed minus expected, and then squared all of that divided by expected. This is the same formula that we saw at the very beginning. My observed count for blue was 26. My expected count was 21.6. And then here in the denominator I also have 21.6. My observed count for brown was 11. My expected count is 12.6, and in the denominator I have that expected count of 12.6. Notice that unlike the first time we used this formula, our denominators now aren't all the same, so it's not as obvious which one is going to make the largest contribution to chi-square. It's not necessarily the one that's furthest away. We can see that having a smaller expected count is going to result in a larger overall value. So let's calculate the first couple of these. 26 minus 21.6. Evaluate, then square, then divide. That gives me 0.896. And looking at brown here, we have 11 minus 12.6. Evaluate, square, remember it always becomes positive, and then divided by that 12.6. So I get 0.203. Now I can see in this case we end up with not nearly as large a chi-square test statistic because my sample wasn't as far off from these numbers as it was from the numbers we got by equal proportions. So now we have a very small chi-square test statistic, which means it looks like it's probably not very strong evidence against the null hypothesis. But before I conclude that, I want to look at it in the graph with the correct degrees of freedom. So this graph again is generated with 5 degrees of freedom. My chi-square test statistic is way over here. Chi-square equals 2.544. My p-value still comes from the right tail, which is going to be a pretty large area. And I just had a little fun with my paint bucket tool and managed to fill that whole thing in red. We can absolutely tell that this p-value is huge, right? It's greater than 0.5. At that point, I don't really care what it is, but I'll go ahead and call it 0.7, something like that. It's somewhere between 0.5 and 1. And my conclusion is that we have no evidence at all that the actual proportions differ from what is published by the M&M Mars Corporation. So this is my conclusion based on the p-value. We have no evidence of any difference. We have not rejected the null hypothesis. The null hypothesis might well be true. If this is the case, we do not need a part 2 of our conclusion. We only really have a part 2 if we got some sort of statistically significant evidence in our part 1. It doesn't really make sense to say we have no evidence that there's any difference, but the largest contribution to the chi-square test statistic was blue. Who cares, right? We have no evidence of a difference, so there's no point going into our data and trying to figure out where that difference is if the difference isn't actually there. So no part 2 if we fail to reject. We only have part 2 if we reject the null hypothesis. And it doesn't have to be a formal rejection. I would say any p-value that is small enough that we would reject at, say, the 0.1 level, right? If we're rejecting at the 0.1 level, if there's no statistical significance level stated, 0.1 is pretty much where we would make that decision point about whether we should provide a part 2 of our conclusion if we weren't given a specific value of alpha. So only if we reject or if we get some level of evidence against the null hypothesis would we include a part 2. We can also pretty clearly see that there's not much point going into StatKey and seeing if our estimate of the p-value was just right? Even if we're way off, there's still no evidence.